In 6.4, we are going to talk about the graphs of logarithmic functions. Now, unlike the graphs of exponentials, where you can really plug in anything because their domain is all real numbers, for these we have to be a little more careful when plugging in. So, things to remember. This is what our exponential graph looks like. And there was a horizontal asymptote. This is what our logarithm graph looks like. And you can see it as an inverse function. If you fold it across the line, y equals x, you get the same thing. So this is our main logarithmic function general form. So this a number could possibly flip it, stretch it. There's your base. This could move it left or right. This will move it up or down. Now, the thing you want to really remember is the domain is always where the inside function is greater than 0. So that's really important that you know that. So make sure you have this function written down, and you add that little note that the inside has to be greater than 0. So since they're inverse functions, the domain of a logarithm will be the range of our exponential. The range of a logarithm will be the domain of our exponential. So the range, it goes up and down from negative infinity to positive infinity. The range, it actually will have a vertical asymptote. So our exponential had a horizontal asymptote. This one will have a vertical asymptote. So it says identify the domain. Anytime you want to know the domain of a logarithmic shift or a logarithmic function that has shifted, a few things we're going to do. We're going to find the vertical asymptote, and then we're going to find the domain. So the vertical asymptote is where the inside equals 0. The domain is where the inside is greater than 0. So that inside of our function determines both of those things. So you kind of get them both for free. So this first one, we have a vertical asymptote at -3. Our graph are the x's that are greater than -3. Now that's good if I wanted it into kind of like set notation or inequality notation, but I want it as an interval. So if we think on the number line, it can almost be at -3, but it can keep on going. So let's do it again. So where's our vertical asymptote? Well, where is 5 minus 2x equal to 0? And then you're going to just solve for x. So we get -2x is -5. So x is 5 over 2, or 2.5. So our domain is very much dependent upon that 5/2. Our domain is where the inside is greater than 0. So if you move the -5 over, or it becomes -5 when it moves over, you have to be careful because when you divide by -2, we have to turn that symbol. So our x is less than 5/2, or it goes from -infinity up to 5/2. Now be careful with that. Why did this happen? Well, we subtracted the x and a number, so that's going to move it over to the right. But our x was negative, so that flips it across the y-axis. So most logarithmic functions kind of have some kind of vertical asymptote like that, but this one moved over and then goes like that. So kind of interesting how that happened. So vertical asymptote of our function is always where the inside equals 0. The domain of our function is where the inside is greater than or equal to 0. So make yourself a note that the vertical asymptote is where the inside equals 0. The domain is where the inside is greater than 0. And watch your rules of inequalities. If you have to divide by a negative, you're going to have to turn that symbol. So those are your answers there. And now let's go ahead and just look at the generals of the graph. It is a one-to-one function. It is the inverse of our exponential. It has a vertical asymptote wherever the inside of the function equals 0. If our b is positive and greater than 1, it's going to go uphill. And if it's going downhill, it had a b that was some fractional number between 0 and 1. It will have an x-intercept at 1, 0. The domain goes from 0 to infinity, but the range stretches. And you notice that's the exact reverse of our parent exponential function. So like any function, if we change one aspect of the function, we're going to change something of the graph. So if we look here, this is a log base 10. That is in orange here. That is our lowest graph. So probably a log base 5 might be here, and a log base 3 might be here. This is a natural log which is a log base e, and e is that 2.7 number. And here's the log base 2. Okay. So you can tell as the bases get smaller, the graph gets a little steeper. So let's take a look at how we graph it. Well, if this is a very simple one, like a log base 5 of x, our x's, we need to be very specific. We need to pick x's that we could do without a calculator. So you're going to pick the reciprocal of our base, 1 and our base. The flip of your base, 1 and your base. Now, why do we do that? Well, the log base 5 of 1/5, what power would I put on a 5 to make it its reciprocal is -1. What power do I put on a 5 to make it 1? Well, that would be 0. What power would I put on a 5 to keep it a 5? That would be 1. So you might recall when we did exponentials, these were our x's. These are our y's. Well, what does a inverse function do? It flip-flops the x's and y's. So that's exactly what happened. So I need to plug in things that I know how to take the log base 5 of. So I use the reciprocal 1 and the original. So let's graph it. Now the vertical asymptote is going to happen where x equals 0, the inside equals 0. So let's go ahead and put our axes on here. And let's put a vertical asymptote at 0. Now, the domain is going to be where the inside is greater than 0. So that's just going to be from 0 to infinity. So that means that the graph lives over here. And our points live over there. 1/5 is at -1. So just you're going to have to guesstimate that one. 1 is at 0. 5 is at 1. So our graph looks something like that. Okay. Now what is the range? The range will always be all real numbers. I can go as low as I want. I can go as high as I want. And you can tell I go low values very quickly. My high values, it's going to take me a while to really get to, even anything higher than a 3. But I can eventually. That's going to keep rising. So that is graphing a very basic logarithmic function. Just like any function, if you add on the inside, it's going to scooch it to the left, and it will scooch that vertical asymptote. If you subtract on the inside, it's going to scooch it to the right, and it will also move that vertical asymptote to the right. So always the key, no matter what, is take your vertical asymptote. It's always going to be the inside equals 0. The domain is always going to be where the inside is greater than 0, and then the range is always going to be negative infinity to positive infinity. And if you know where the inside is equal to 0, that will help you find your domain. So add on the inside moves it left, move that vertical asymptote. Subtract on the inside moves it right, move that vertical asymptote. So here we have one where there has been a shift. Now it says to graph it along with its parent function. So I'm going to call the parent function g of x, which is just the log base 3 of x. Okay. Now let's put the parent function on. Now it's a log base 3, so I'm going to plug in 1/3, 1, and 3. I'm going to get out -1, 0, and 1. So I'm going to just put that over here in red. There is a vertical asymptote at 0. At 1/3, I'm at -1. At 1, I'm at 0. And at 3, I am at 1. Okay, so now we got our parent on there. Now let's focus on the new function. Now the new function, we have that -2. So this entire graph is going to move to the right too. So the asymptote will move, and each one of these points will jump over to the right too. But let me show you why. So let's take our x minus 2 and think to ourselves, when am I going to get 1/3? When am I going to get 1? And when am I going to get 3? The 3 original good versions of something to plug in to a log base 3. You'll notice each one of these x values we're going to add on 2. So this is 2 1/3. This is 3. And this is 5. So for our f function, we want to plug in 2 1/3, 3, and 5. Now, there's nothing on the outside of the function. So if we plug in 2 1/3, we get 1/3, which gives me a -1. What power do I put on a 3 to get 1/3? 1, -1. And then this one's going to give me 0, and this one's going to give me 1. Now, where's our vertical asymptote? Well, that's where the inside equals 0 because we've added 2 onto everything. So we should expect that it's at 2. So let's put it on the graph paper. We have some really nice points. Let's put those on there. And so at 2.3 or 2 1/3, we're down at -1. At 3, we're at 0. At 5, we are at 1. So what you should have expected happens, expected. It moved to the right 2 units. Okay, now the only thing we have to talk about is domain and range. The domain of this graph starts just on the right side of 2 and keeps going to infinity. Remember, that's where the inside is greater than 0. So where x is greater than 2, so 2 to infinity. The range is all real numbers. So that is one that's a little more complicated. So just make yourself a note that this one has moved to the left 4. And just let's make a general, real quick graph, because we have quite a few others to do. The graph looks something like that. Okay, so let's just move on from that one. So remember, if we move something or add something on the outside, it's going to lift it up. If we subtract on the outside, it's going to move it down. So now let's look at this function. So we can put on that parent function already. We know what that parent function looks like. That log base 3 had a vertical asymptote at 0. At 1/3 it was down at -1. At 1 it was at 0. And at 3 it was at 1. So that's the parent. Now what the -2 is going to do is it's going to take our parent function, which was 1/3, 1 and 3. We got -1, 0, and 1. And it's going to -2 from each of those. So all we got to do is take our original function and move all of these values down 2. The vertical asymptote kind of slides down as well, so it would still be in that exact location. If you put a number on the outside that is more than 1, it's going to stretch it higher. It's a vertical stretch. If you put a fraction that is between 0 and 1, it's going to pull it downward. It's going to kind of smash it closer to the x-axis, stretch it further away from the x-axis. So let's do this one. So our parent function, I'll call g of x, is just log base 4 of x. So I would plug into that 1/4, 1, and 4 to get my -1, 0, and 1. So let's put that on there. Your vertical asymptote is at 0. My points are 1/4 is down at -1. 1 is at 0. 4 is at 1. It's down just a little bit further than our log base 3 graph would be. And all that's going to happen for this function, since our x hasn't changed, our x is still just an x, we are going to still get to plug in 1/4, 1, and 4. Initially, we still will get out -1, 0, and 1, but there's just that 2 out there. So if you follow order of operation, that 2 on the outside will just multiply these values by 2. So it's going to just stretch it a little higher than it originally was. So this is going to be at -2. Well, it's going to stretch it 2 times further away from the x-axis. And this is going to be 0, and this is going to be 2. So at 1/4 now, instead of at -1, we're at -2. At 1, we're still at 0. And at 4, now we are at 2. So it's just kind of stretched it out a little bit. that 2 lifted it twice as high or stretched it down twice as low. The vertical asymptote is still at 0. The domain is going to go from 0 to infinity. The range is still all real numbers. Because we didn't change anything on the x. The x still says an x. Let's skip this one. Let's talk about how we flip it. Just like anything, if we put a negative on the outside, it is going to flip it over the x-axis. So in red is our original. If you put a negative on the outside, it flips it across the x-axis. If I put a negative on the inside, it flips it over the y-axis, and that's what's happened here. So here, this is a log base 10. Let's not worry about the parent function. Let's just worry about this function. So it's a power of 10. So I'm going to plug in 1/10, 1 and 10, so that I get out -1, 0, and 1. But there's a negative on the outside. So let's put a negative on the outside. So we get 1, we get 0, we get -1. So it's flipped it. Now let's graph it. We still have a vertical asymptote at 0. So let's put that on there. At 1/10, we are at 1. At 1, we are at 0. And at 10, we are down at -1. So what should have been like this flipped over the x-axis. So just remember all the things that can happen to a function that are listed here, but the inside is going to affect our x, the outside is going to affect our y. You have to be very, very mindful as to what you plug in so that you get nice values. These ones you have to be a little more careful about the x's that you choose. So last thing is to find our vertical asymptotes. So all we care about is this number here. So where does x plus 4 equal 0? That's at -4. Now let's discuss what happened to this graph. It has moved to the left 4. It has been flipped and stretched, and then it moved up 5. So lots of things happened here. The only thing that's going to affect our second one's vertical asymptote is right here. So just set x minus 1 equal to 0 and get 1. And that is your vertical asymptote. What has happened to this function? Well, it moved to the right one, and this plus 3 moved it up 3. I would probably put the plus 3 over there. That would be helpful. Okay. And then you have some graphs to do, and a little bit of algebra talking about domain and range. So there you go. There's some log graphing. There is 6, 4.